Okay, today is our great pleasure to have Lena Funcke from Bonn University. Lena got her PhD from Ludwig-Maximilian University in Munich, and also in the Max Planck Institute. And then she was doing postdoc work at the Parameter Institute and MIT before he joined the Bonn University. And today, she's going to tell us about her work on the Hamiltonian lattice formulation of compact Maxwell-Chern-Simons theory. So, Lena, the stage is yours.
Yeah, thank you very much for the kind introduction. Thanks a lot for the invitation. It's a great pleasure for me to speak here today. So good morning and good evening, like depending on where all the online people are in the world. I'm very much looking forward to discussing this work with you. So this is based on a recent paper that we put on the archive in the summer this year, like right before the Lattice conference. And it's about a Hamiltonian lattice formulation of compact Maxwell-Chern-Simons theory. And our goal is to eventually being able to simulate this on a quantum computer. And this is why I chose this topic for the IQuS research seminar series today. But we're not there yet. So it's still like very much on the analytical side right now. Okay, so I will. Okay. So let me start. So why are we interested in Hamiltonian simulations of topological terms? So you all are very well familiar with the sign problem, I guess, of Markov chain Monte Carlo methods. So what usually is the standard approach for discretizing gauge theories on a lattice is to go to Euclidean space-time, discretize the theory, and then use Markov chain Monte Carlo sampling of the resulting path integral. However, if we have topological terms, then in Euclidean spacetime, the term picks up an I, and so therefore the action becomes complex. It's not real anymore. And then we cannot really sample path integral configurations anymore. And this is the infamous sign problem of Markov chain Monte Carlo, which also hinders the simulation of finite density systems. And there are some workarounds for the Hamiltonian approach. So, for example, one can make a contour deformation of the path integral. One can also use machine learning, for example, to learn Lefschetz symbols and so on. But none of these approaches have so far resulted really in a complete circumvention of the sign problem. And this is one of the big motivations of looking into alternatives, and in particular into Hamiltonian-based simulation methods. And there are several different ones on the market. For example, tensor networks. So here, the reason why the sign problem is circumvented is that observables are computed in a very different way. So we're not actually interested in the path integral, but we are interested in just approximating the quantum state itself. And then we compute observables by simply taking expectation values of operators with respect to the quantum state of interest, which could be, for example, the ground state of a system. And so a tensor network approach is simply an approach to parameterize it's an entanglement-based answers for the wave function. It's an approximation which works very efficiently if we have low entanglement in the system. And so what has been done there, so I'm highlighting here some works that we've done on also works other people have done on simulations of topological terms in 1+1 dimensions. For example, a theta term in compact quantum electrodynamics, or the Schwinger model, which is a model that has a lot of similarities with 3+1 dimensional QCD, like confinement, chiral symmetry breaking, chiral anomaly, a theta term, and so on and so forth. And we also looked at a theta term in the CP1 model, which is interesting for studying, for example, Haldane's conjecture. So tensor networks, they work very efficiently in 1+1 dimensions, and there have been first ansatz already in 2+1 and 3+1D, but there we still struggle with finding a computationally efficient approach for really simulating the sign problem afflicted regimes, and topological terms have never been simulated in high dimensions with tensor networks. And the same is true for quantum computing. So there have been first simulations of theta terms also for 1+1D compact quantum electrodynamics, but also not yet anything in higher dimensions. So If we want to actually go to higher dimensions, one first step that we have done a couple of years ago is to first of all formulate a lattice Hamiltonian in the Hamiltonian formulation with the theta term in 3+1 dimensions. So here we focused on compact U1 gauge theory. And we also had some first numerical results, which I show you on the right-hand side. So as I say here, it's exact diagonalization. So we cannot access large system sizes. So this is simply one single cube with periodic boundary conditions. But it's actually the first time that a 3+1 dimensional theta term has been numerically investigated for large values of the theta parameter. And if we now look at an observable here, topological charge as a function of theta, what we actually see is signs of a phase transition for large values of the coupling G corresponding to small values of theta, which is 1 over G squared. So these are the red data points here. And you would expect to see a phase transition at theta equal to pi, which is also a transition you would expect in QCD in 3+1 dimensions. But you see it's shifted to non-pi values of theta. And this is very likely due to the small system size, and it's motivating then tensor network and quantum computing simulations of this system. So when you look here at the state of the art, what you see is topological terms have been studied numerically in 1+1 and in 3+1 dimensions. However, not yet in 2+1 dimensions. And then the question is, why is this the case? So this is a question that we asked ourselves a couple of years ago, because with our methods of tensor networks and quantum computing, we wanted to go to higher and higher dimensions, and we skipped 2+1D. And the reason actually is that at that time, no suitable lattice formulation of a topological term in 2+1D had been available. So why are these topological terms in 2+1D actually interesting, and how are they different from topological terms in 1+1 and 3+1D? So the biggest difference is that in 1+1 and 3+1D, we have a theta term, while in 2+1D we don't. There we have a Chern-Simons term, and these terms have very different properties. So the people from the more high energy physics, nuclear physics community will be very familiar with the left-hand side, while the condensed matter people will be very familiar with the right-hand side. I guess the audience is more on the left-hand side. So let me just explain to you the motivation for looking into these Chern-Simons terms. So the relevance of theta terms is, for example, within the standard model, the strong CP problem of QCD, but also within grand unified theories where we have a larger compact gauge group, we can get theta terms also beyond QCD. While in 2+1 dimensions, it's Chern-Simons term is relevant for the quantum Hall effect, for fermion boson dualities, and so on. The parameters of these terms are very different. So for a theta term, we have a continuous theta angle going from 0 to pi, while for the Chern-Simons terms, we have a quantized Chern-Simons coupling, K, which is called the Chern-Simons level. Also, the consequences of these terms are very different. So in 3+1 dimensions, the theta term does not yield any degeneracy of the ground state, while in 2+1 dimensions, the ground state actually has a k-fold degeneracy on a torus. So if we look at the system with periodic boundary conditions, for example, in the two spatial dimensions, then we get a k-fold degeneracy. So in general, we have a k to the power of g-fold degeneracy for a manifold with genus G. Another consequence that's very interesting for the Chern-Simons term is that it generates mass. So we know in 3+1 dimensions that masses are generated through the Higgs and QCD sectors, but there's no mass generation from the theta term itself. In 2+1 dimensions, we can actually get a photon mass from a Chern-Simons term. So if we have QED, or we just have Maxwell theory without fermions, and we have a Chern-Simons term, then the photon acquires a mass that's proportional to the Chern-Simons coupling K, as you see here. And this theory of U1 gauge theory with the Chern-Simons term is called Maxwell-Chern-Simons theory. And this is the theory that we were interested in our paper. And what we were interested in is to see is whether we can actually derive a lattice formulation that can like reproduce these known topological features of having a quantized Chern-Simons coupling, the degeneracy, and the mass generation. So we should like keep these three things in the back of your minds, and we will come back to this later at the end of the talk and see that we can actually reproduce these features. Another motivation for looking into Maxwell-Chern-Simons theory is that if we look at pure Chern-Simons theory, we have a doubling problem, which is very similar to the fermionic doubling problem once we put fermions on a lattice. So the same is true for Chern-Simons theory on a lattice. And if we add a Maxwell term, this doubling problem can actually be eliminated. Okay, so how can one formulate Maxwell-Chern-Simons theory on the lattice? So let's look at the problem and let's look at the state of the art of the previous approaches that people have looked into. So when we look at the continuum version of the 2 + 1 Chern-Simons term, you see some similarities and differences to the theta term that you're probably more familiar with. So you see an epsilon tensor as we have in 2 + 1D, but then the structure of the gauge fields looks very different. So A is the 2 + 1D U1 gauge field in this particular case, and K is simply the Chern-Simons coupling that we previously discussed. So now if we look at a naive lattice discretization, we replace the integral by a sum over the different sides. We replace D by the finite difference operator delta, and we get our finite lattice spacing A in here. And we immediately encounter a problem, namely if we consider compact gauge fields, we have monopoles on the lattice, and the Chern-Simons term is known to violate gauge invariance in the presence of monopoles. And if you want to know about how this works, why this is the case, I have some backup slides on this. And so this has been an open problem now for a couple of decades. So then what's the state of the art of then really trying to formulate a more than naive lattice discretization of Chern-Simons theory? So there has been in the 80s by Lucia a lattice formulation of non-compact Maxwell-Chern-Simons theory in the Hamiltonian formulation. However, it's a non-compact version. So it's not straightforward to just take that Hamiltonian and really simulate this numerically with the methods that I've mentioned earlier on. So then there has been lots of work going on in the last decades. So one I would like to highlight particularly, because it was very important also for our paper, is the first lattice formulation of compact Chern-Simons theory and the Hamiltonian formulation that uses the Willem approach in order to eliminate the monopoles. And therefore, the theory then eventually becomes gauge invariant. And so our theory also requires the Willem approach to our formulation. And so this was really an important stepping stone in this paper here that was published this year. However, what they have is a non-commuting geometry. So the gauge fields on the different links, they don't commute with each other. And we have the issue that, as I mentioned earlier on, the Chern-Simons theory without the Maxwell term has the doubling problem, similar to a doubling problem that we have in the fermionic sector. And it can be eliminated by adding a Maxwell term. And so this is then our goal. So the goal was to derive a compact version of a Maxwell-Chern-Simons lattice Hamiltonian in order to pave the way for simulations using, for example, tensor networks on classical computers or quantum algorithms on quantum computers. So let's jump straight to the results. And if you have some questions on the details of how we got there, I have some backup slides on this as well. So the interesting observation that we made is that the result for the compact Maxwell-Chern-Simons lattice Hamiltonian is actually the same as the very well-known result for 2 + 1D Maxwell lattice Hamiltonian, so without the Chern-Simons term, plus an extension. And this is exactly the Chern-Simons extension. This is how the Hamiltonian looks like. And I will go in more detail into what the different terms mean. I just want to, at this point, make a comment on the notation here. So you see the dashed lines and the solid ones. So we have two spaces plane, and we look now in this slide, from top on this plane. So these are the two dimensions that we have, the two spatial ones. And these dashed lines are only as a visual guidance for your eye, that if we have this terming, for example, and due to the square, we have some mixed terms, the mixed term will be this prefactor multiplying A2 on that link and P1 on that link. And so here, this is just as a guidance for your eye. And I really like this graphical representation of the Hamiltonian, because you can then directly see like how the different terms in the Hamiltonian enter at which sides. So I mean, there's also a way of just writing down the equation, but I find this visual representation much more easy to follow. So now let's look at the different terms. Let's look first.
Can you explain this line one more time?
Okay, yeah. So what it is basically, what it means is that so if we have, so usually what we're known, for like standard Maxwell-Lattice Hamiltonian, we have basically E squared plus B squared, right? And this is basically, so the P's are E squared, these terms, and this is the B squared. I will go more into detail in a few minutes. But what we would do is we would sum over all the different things, right? So we have a summation over the links in the X direction and in the Y direction. This is what we have. And so I chose this graphical representation to show that we have these mixed terms where we have P1 going into X direction and A2 going into Y direction. And they actually get mixed. So we have terms that mix X and Y in here. So this is that representation. Does it make sense?
Okay, so the dashed line just help to indicate these two terms mix.
Exactly, yeah. So the dashed lines means that here there's no contribution. So we simply have P1 in the X direction here in the first term, and we have A2 in the Y direction. And the dashed line is just there to show you where the P1 would couple to the A2 in the mixed terms we have here because of this term.
But,
yes.
but in this square, does the P1, do you have a quadratic term in P1 and also a quadratic term in A2?
Yes, exactly. So it's P1 squared, and we have A1, because we sum over all, so the A1 squared is here. So we have like A2 squared and A1 squared, and then we have P2 and P1 squared. So we have the squares in like all directions of the lattice. And then we have these mixed terms between P1, A2 and P2, A1.
Okay.
Yeah.
Okay. Thank you.
Yeah. Yeah, thanks for the question. Yeah, feel free to interrupt me at any time if you have some questions. I could also like show you. No, let's do maybe at the end. So I also have like an explicit backup slide on like the just like how the equations relate to the graphical notation, but yeah, I think maybe it's now after the explanation obvious. And I think you also will get the slides, right? Do you upload them as well? Or
yeah, we can try to do that.
Okay, yeah. Okay, but if you want to see like the equation as well, like let me know. I have a backup slide and I can just show it to you. Yeah. Okay. So what I wanted to discuss here is let's first look at the magnetic field term, because it is exactly the same as we have for quantum electromolecular, or if we don't look at fermions, simply just the Maxwell part of it. So if we have just Maxwell or QED, we get this just the famous 1 minus cosine of the packet. If one now uses the Wien approximation, which one has to use in order to eliminate the monopoles, because I mentioned in the slide before, we have to get rid of the monopoles, because if we have monopoles and then we add a Chern-Simons term, we violate gauge invariance. So we have to suppress the monopoles. And it has been known for some time that if we do that, this 1 minus cosine of the plaquette reduces to plaquette squared. And this is exactly the term that you see down here in brown. So that's just exactly the same as we have it in QED. And now if we look at the electric field term, so the brown boxes here highlight that this is exactly the same as in QED with the Wien approximation without the monopoles. So we have P squared plus the packet squared, which is basically E squared plus B squared of like just continuing Maxwell Hamiltonian. And then there's a modification due to the Chern-Simons term. And this modification only enters through the electric field term. This was already known a long time ago, like also in Lucha's paper in the 80s. The magnetic term stayed the same, and the only term that got modified was the electric field term. And the modification, as you see, is exactly this very interesting structure of coupling like the gauge fields to the conjugate momenta on like adjacent sides. And you see the Chern-Simons coupling K here and the lattice coupling A as prefetch. The commutation relations for A and P are just the standard ones that you all know, so with I delta X Y. And the compactness comes through the constraints on the Hilbert space. So the gauge configurations A, they can actually take values from minus to plus infinity. Because, so if we had the standard compact QED without the Wellen approximation and with the monopoles, we would have this cosine structure, which would ensure the compactification. But if we then have the Wellen approximation to suppress the monopoles, we get rid of the cosine structure. So the gauge configurations, they can take values in minus to plus infinity, but then the compactness enters through constraints on the Hilbert space. And so this is exactly the same as we know from quantum electrodynamics in 2+1 dimensions with just the Wellen approximation, with suppressing the monopoles. So this is all very well known. So this is not anything that we added to this. The only thing we really added is to find out how to modify this Hamiltonian in order to get a Chern-Simons term. And this is simply this, these two terms here. So this is the whole basically novelty of the paper are just these two terms. So yeah, and then like conceptually understanding like how this can be derived and related then to the Lagrangian formulations obtained earlier on. Okay, so when you look at this Hamiltonian, you might be a bit disappointed because it's quadratic, and so you can solve it analytically. And so at least I was a bit disappointed when I first saw it. I thought, oh, then I wanted to do something numerical. I wanted to simulate the system. Now we can solve it analytically. So all the numerical methods I mentioned on earlier, like tensor networks, quantum algorithms, or even like machine learning algorithms for learning quantum states, we don't really need them, right? When looking at the Hamiltonian, it's just analytically solvable. However, once you add fermions to the theory, and then things become really interesting also for experiments, then this Hamiltonian can't be solved analytically anymore. And so this rescues us, and this is some ongoing work that we do right now to add fermions to the system. So Wilson or staggered. And then this is really the point where numerical methods become relevant. But yeah, so this analytical solution now that one can obtain is actually very important for cross-checking whether this Hamiltonian actually makes sense and actually has the topological properties that we want to have, that I mentioned earlier on in the very beginning of my slide, in the very beginning of my talk. So let's look at this exact solution of the lattice Hamiltonian, and we can compare there the pure Maxwell theory and then the Maxwell-Chern-Simons one, so the modification of the Maxwell theory. So for pure Maxwell theory, what we would expect is to have a linear dispersion relation of a gapless photon. So we have delta E, which is the gap. Then we have the momenta, Q1 and Q2. So these are the dimensionless lattice momenta. So A times Q tilde, where Q tilde is the dimension for momentum. And so what we would expect to have like a linear dispersion relation as we see here. And this is what we get. So if we look at the plot of, so this plot here is the dispersion relation that we computed from this exact analytical solution of the lattice Hamiltonian. So this is delta E, it's the gap given by omega, which is the square root of the first term, which is simply the standard Maxwell contribution. So we have Q1 and Q2. You see that for small q's, you can expand, and you get a q squared, and due to the square root, you just get a linear behavior here. But this gets modified, as before, by a Chern-Simons. And what we see is that the Chern-Simons term generates a gap. So if you look at the plot here, you see it doesn't go to 0. It goes to 1 in these particular units. And so you see that there is a gap opened, which is exactly due to this Chern-Simons term that does not vanish for Q1 and Q2 going to 0. And so now the question is whether this formula that we obtained on the lattice for finite A, which enters here and which also enters in Q1 and Q2, whether you can actually, when you take the continuum limit, now get the mass that was predicted earlier on for the continuum version of Maxwell-Chern-Simons theory some decades ago. And it turns out that this is exactly the mass given here. So if you take the continuum limit, the first term vanishes, and the second term reduces simply to an identity. And so what you get is this term here in the bracket. And so that is like an answer to the first of the threefold question of whether we can, yeah.
Can you go back to the previous slide?
Yes.
So in the standard Higgs mechanism that I know, it's the constant that saves you from the gauge invariance, and then you still get a mass. And I'm having a little trouble mapping in Chern-Simons case. You have one version of lattice Hamiltonian, which gives you a mass, and you have a different kind of mechanism, topological mechanism in the continuum limit that gives the mass. And can you comment on how those two are related for the Chern-Simons case?
I didn't acoustically get like some words of the first part of your question, but so you were asking that whether there's like a different generation of the mass for the lattice and the continuum. It's exactly the same generation. It's the same mechanism.
For the Chern-Simons case? Okay.
Yes. Yeah, it's exactly the same. Yeah. So what happens is that if you look at this lattice Hamiltonian that we have here, and then you simply just solve this quadratic Hamiltonian. So having this Chern-Simons contribution here in the E field means you have a massless photon field. And so this is what you then directly see when obtaining the dispersion relation. And if you want to then take the continuum limit, what you get, because Q is simply A times Q tilde, where Q tilde is the dimension for momentum. So then you get factors here of A squared, Q squared, which is I know it's exactly the opposite. So it's Q tilde divided by A. Yeah, and so then wait a minute. So I just mixed it up. So yeah, no, so Q is A times Q tilde, and so if you let A go into infinity, then only the square term survives. Yeah. And so only this term here, the second one survives. So I can show you the results here. So this is like the term surviving from the Chern-Simons term from the second part, and this is the first Q tilde surviving here from the cosines there. Yeah.
Yeah, Rob, you have a comment?
But the Chern-Simons term is parity odd. Presumably that's because it's hidden in because it's Q1 plus Q2. I was just wondering where the Chern-Simons mass being parity odd shows up in your expression for the dispersion relation.
So you mean in the continuum? So when you just take A going to zeros, then what you would get is like the Q tilde, so the dimension for momentum squared, and you get just K times E squared over 2 pi squared from the previous from the Chern-Simons modification. And this is, yeah. What was this your question? Or
the Chern-Simons is parity odd.
Yes.
So that's because it's you don't get the same mass if you flip the sign of Q1 or Q2 as you did for the.
So you mean it should be parity odd? So you say that there should be some
parity odd.
So you say there should be some relative minus sign somewhere in there.
No, I'm just asking how it shows up. Maybe it just doesn't show up in the dispersion because there's a handedness to the term.
Yeah, that's true. It's actually a very good point. Yeah, we didn't think about this. That's true. There should be, if it shows up in the dispersion relation, there should be a relative minus sign here because.
Well, I don't know. Okay, it was just a question. It's not important.
Yeah. So we haven't thought about this before, but I should. We should. So I will note it down, and if I have an answer to that question, I'll let you know. Yeah. Yeah, we actually didn't deeply think about like the signs of the different Q1s and Q2s in the dispersion relation, but that's a good point. Yeah. Okay. So, yeah, so I wanted to raise the question whether we can correctly reproduce all the topological properties. And I wanted to make a disclaimer. So there are some properties that I don't talk about in the talk today. So one can also reproduce like non-trivial properties of the Wilson loops, and there are some mutual and self-statistics of anyons and so on and so forth. But this goes very deep into condensed matter physics, and I skipped it in the talk today just because I was assuming most of you are from the high energy physics side. So I reproduce the topological properties that I think are then more familiar to this audience. So what I focus on is exactly this photon mass and quantized coupling and ground state degeneracy that I mentioned earlier on in the talk. Yeah, this is one thing that we already discussed. So the continuum limit of the dispersion relation, if we take it, then we get a correctly reproduced photon mass in the continuum, which was shown earlier on in the 80s. So this is exactly the expression that we see here in green. The second question was whether we can correctly reproduce the quantization of the Chern-Simons level. And there, I mentioned earlier on that we have these large gauge transformations that ensure the compactification of the gauge fields. And so these generators of the large gauge transformations, L1 and L2, if we, they unfortunately don't commute, but if we apply L1 first and then L2 or vice versa, we should get exactly the same result. We have the additional constraint that e to the power of 2 pi ik, which is exactly what pops up in the commutator, this has to be equal to 1. And this immediately gives us the quantization condition for the Chern-Simons level k, which we discussed earlier in the beginning of the talk, has to be satisfied for the Maxwell-Chern-Simons theory. And the last thing that we check that I want to discuss is this ground state degeneracy. So if we have a torus, so periodic boundary conditions, like the more numerical people, this is simply just what we do in our everyday life with our simulations, simply not using open but in periodic boundary conditions, we get this torus, and therefore have a non-trivial topology of our manifolds. And I mentioned earlier on that for this it's expected to have a k-fold degeneracy because a torus has a genus of 1. And this is something that we can also correctly reproduce. So we were able to derive this degeneracy of the ground state. And this is something which is actually a good cross-check for numerical methods. So whenever we implement this numerically, just the pure Maxwell-Chern-Simons theory, the first thing we want to look out for is whether the ground state has the k-fold degeneracy, because it's easy to check. One can simply increase the Chern-Simons level k in the simulation and then see how the ground state becomes more and more degenerate. So this is a very important benchmark to know to take the next step of numerical methods. Yeah, and so mentioning numerical methods, it brings me to a summary and outlook. So as a summary, the topological Chern-Simons theorem is relevant for quantum Hall effect, for topological mass generation, for boson dualities, and so on. And what we derived is a Hamiltonian lattice formulation for 2 + 1D compact Maxwell-Chern-Simons theory and an exact solution. And this exact solution showed the correct topological features of the photon mass, quantization of the Chern-Simons level, degeneracy of the ground state, but also the non-trivial properties of Wilson loop and the mutual and self-statistics of anyons, which I haven't talked about so far. And as an outlook, I mentioned that it's the quadratic Hamiltonian, so we can exactly solve it in the pure Maxwell-Chern-Simons case, but once we add fermions, that's not doable anymore. We get actually very rich phase structure, and it would be really interesting to also have them fermions with a chemical potential there, because we have finite density, for example, in the experimental context of quantum Hall effects. And so this is really something that we would be very excited to do, either on classical computers with Kondi networks or with quantum algorithms. So generally with Hamiltonian-based simulations, because we have no exact solutions there. And so for more details, you can look at our archive article, which came out in July this year. And this is what brings me to the end. I would like to thank our collaborators, and I would like to highlight the work of Chan Yang, who basically really did the essence of this work. So he did a really great job at doing lots of all these derivations. So yeah, I want to give like all the credits to him here. And yeah, so this is the whole crew of our collaborators, and I would like to thank them and our group. And thank you all for listening. And if you have more questions, I'm happy to discuss now.
One question. Okay, maybe I can start with, can you actually explain to us why the monopole kind of leads to the violation of the gauge invariance from the Chern-Simons term?
Yeah. So I thought I had a backup slide on this. Yeah. So I mean, yeah, generally, so we have the monopole problem. Like I had a backup slide on saying like, okay, where does it come from? Yeah, I don't know. I have it actually in here. So what happens is, yeah, so if you have your monopole configuration, what you have is, if you look at large gauge transformations, you actually get a change in the Chern-Simons action. So you get boundary terms at spatial infinity, and then the action violates gauge invariance. So this is, I thought I maybe have some equations on this, but yeah, this was shown. I hope that answers your question. Yeah, it's actually kind of similar to what we know in 3+1 here as well. But there of course, if that term doesn't violate. Yeah.
So it violates gauge invariance because of the boundary terms.
It's spatial infinity. Yeah.
Can we see your backup slide on that? Because as I remember, I thought you quantized the coefficient of the abelian term in units of the magnetic charge. Am I mistaken?
You quantize the Chern-Simons level, but you don't quantize. What do you mean with the coefficients? You don't quantize the coupling for the gauge.
Could you show us your backup slides?
On what exactly?
On the coupling to a monopole.
Yeah, I actually don't have it here. I'm sorry. I thought I had it here. It was just this. It's just like this very old result from the 80s that if you have a monopole configuration, then you violate gauge invariance. But in our setup, we have the villain approach that suppresses the monopoles. So the monopoles are actually eliminated in our setup. Because yeah, I mean, we want to have a theory that is not violating gauge invariance, and therefore, yeah. So that's why I didn't have a backup slide on that, because it's just like the motivation for actually using the villain approach, but then in our approach, yeah, we have monopole suppressed, and therefore we don't have this issue of gauge invariance violation.
Yeah, no, okay. If you suppress the monopoles, then you don't have a problem.
Yeah, I think if we don't suppress them, we have a problem. I mean, we can't formulate this theory consistently. No.
Yeah, because I just wanted to comment that people like Alexei Chairman, Theo Jacobson, Jingwan Chen have been working very hard on that. But it involves things like category theory, and it gets a little hairy. It gets very hairy.
I had some discussions with Alexei about this.
Yeah. Thanks.
Dima, you have a question or comment?
Yes. I also have a question about the monopole sector. So I was wondering if one can look closer at the monopole sector of this theory, because if I recall correctly, and Rob can correct me, there is a monopole confinement, right, in 2+1 Maxwell-Chern-Simons. I mean, not confinement due to monopoles, but confinement of monopoles and anti-monopoles. So
I believe so. Yeah.
So it would be very interesting to try to detect this phenomenon, because I don't think it was kind of ever simulated. And another thing, which comes to mind is once you add fermions, then there are kinds of currents that one can look at. So first is the chiral H state, of course, right, which will be set by the sign of the Chern-Simons coefficient. But also, as Rob pointed out, if you have this monopole anti-monopole pair, then you probably will have a current flowing from monopole to anti-monopole along the string that connects this monopole anti-monopole pair. So this I don't think was ever investigated. It's a little bit analogous to chiral magnetic current, but you know it's 2 + 1, so it has somewhat different nature.
That's very interesting, yeah, because we're still looking for things to simulate, and it's not really my background. So I was looking forward to having this discussion to get some ideas there. Also, like, what are really the open questions, things that would be really interesting to simulate. But if you say something like monopole confinement, if we suppress the monopoles, then we cannot actually simulate this, but we could look at actually a theory without the monopole suppression. And then be able to do that.
Okay, great. Thanks.
Yeah, thanks a lot. Yeah.
Any more questions for me?
I don't have much of the knowledge about the topological terms, but I would imagine if you have a pure gauge theory, in a typical other pure gauge theories which have confinement, I would create 2 static charges and try to see how the potential scales. And I'm imagining the mass, if the photon has mass here, it would be exponentially falling. Would it be a good first starting point to check, to include 2 static charges and just check their potential with the separation?
Yes, this is actually something. So we have already done some numerical things. We started like not actually tensor networks or quantum simulations, but they're these Gaussian state. And it is proposed by Ignacio Sirac and Julian Bender and so on. And we have actually one student working on this at Daisy in our collaboration. And so, yeah, it's exactly the first thing that he tested. So he exactly sees that exponentially. So he sees like turning on and off the Chern-Simons spring. He sees turning on and off for fine properties of the field.
Thank you.
But yeah, that's true. Yeah, that was actually the first cross-check. So I said that it would be interesting to look at the ground region. Honestly, the first cross-check was exactly actually to see what happens with confinement.
Yeah, just echo Lena. Actually, today we just talked about this, and exactly as what Lena mentions. Yeah, we check this potential of the when we put 2 static charge there.
So does your construction apply to non-abelian case?
What? I didn't hear.
Oh, the non-abelian Chern-Simons.
So we have a abelian theory at the moment. So we simply have V1. We haven't looked into non-abelian so far. I don't know from the top of my head how this would change the way. No, but that's a good question. I'll keep it in mind.
Okay.
Yeah.
Yeah, if I could comment,
Yeah.
because the non-abelian is much harder, because there you do have a
Okay.
quantization of the coefficient,
Yeah.
and that's why doing it with monopoles is like a baby first step to the non-abelian case. Because then you do have a quantization condition related to the magnetic charge.
Yeah.
And I think Chen and I don't know if it's Jacobson and Sherman, I thought they claimed they had certainly solved the abelian case in general, but I don't remember how they treated monopoles. So they may have suppressed them.
Did they look at Maxwell-Chern-Simons or Chern-Simons?
Maxwell.
Maxwell-Chern-Simons, I see. Yeah. because like a Hamiltonian lattice formulation is really simulatable with like a complex field and so on. So this was not, yeah, but with the monopoles being suppressed, maybe they looked at a situation where they were not suppressed.
Yeah, I don't remember offhand.
Regarding non-abelian, I always thought that the abelian case would be more interesting from a physical perspective, but maybe I'm wrong there. So if you have some insights on that, that would be interesting. So I mean, for actual like quantum Hall effect of the Chern-Simons theory itself would be really interesting.
Yeah.
To take just taking the gauge into there, and then it doesn't really matter if one has like an abelian or an abelian case, right? And so yeah. I mean, of course, one needs the term to like the doubling problem, but what kind of additional value would be there to change the abelian case to non-abelian from a simulation point of view, or like an experimental point of view?
Yeah,
You know?
well, I think the non-abelian is beautiful on its own, but
Oh yeah, sure, yeah. It's just
you know, what do you?
yeah.
Yeah,
Yeah, no, that's good. Yeah. Yeah. I thought there might be like some additional for looking there. I mean, of course, in 3+1D, understand how it's obvious, but for 2+1D, for like all the condensed context, I always thought like the main motivation was really to just have like an abelian case for important. That's it. Yeah.
Yeah, okay, yeah. Any final questions for Lena? Yeah, if no, let's thank Lena again.
Yeah, thanks a lot for all the comments.
Yeah, thank you very much for joining us today.
Yeah, thanks again for maybe I don't see you. Okay, I think.